Okay, this is the Tautenburg Schmidt telescope. It has an aperture of 2 meters when it's used in the spectroscopy mode, and we can convert it into a Schmidt telescope by adding a Schmidt corrector plate of 1.34 m in aperture, which is a glass plate. And in the imaging mode, the focal length is 4 meters, and we use it together with a CCD camera, which has a field of view of 50 by 50 arc minutes. So the telescope is optimized for wide field applications. So in order to search for interesting objects or to observe very extended objects. What we have done so far are a large number of projects. One is, of course, searching for minor planets, and today we are also following up minor planets where the orbits are not so well determined, and that's a very nice application for this telescope. Other programs are, for example, studying gamma ray bursts which suddenly explode and to follow them up. And then also looking for outflows of young stars. During full moon time, we converted to the Coude mode, which is equipped with a high resolution shell spectrograph with a resolution of 65,000. It's a relatively new spectrograph, and we are using it for searching for extrasolar planets. Actually, we have found a number of extrasolar planets already, and we use it mostly for high precision radio velocity work, and a little bit more than half the time it's used in spectroscopy. We also have a third spectrograph which we use in the Naismith focus, and this is the so-called faint object spectrograph, which is basically to observe relatively faint objects, faint stars and galaxies and so far. And what we are also using this spectrograph for is basically spectral typing of faint stars which were recently discovered in the context of the Corot satellite mission, which is searching for extrasolar planets, and we are using this spectrograph for a quick spectral determination. So the telescope is actually used every clear night. Roughly every third night here is clear, and we are using it all the time except Christmas and New Year's. These are the 2 nights which are unscheduled, but otherwise it's every night is used. And at the moment we take observations in about 1,000 hours per year. And it's a very nice telescope. In the last 10 years we have completely refurbished it, and it's now computer controlled and so on. And we are no longer operating it from the dome, but from a heated observer's room, and with new motors and the new encoders. It points also very well. For example, that's very helpful for the gamma ray burst follow-up. There are satellites detecting gamma ray bursts, and they are sending SMS messages to the telescope computer, and then the telescope computer basically says, okay, here's a gamma ray burst, shall I observe it? If you say yes to it, the telescope is pointed at the gamma ray burst, and the dome moves to the correct position, and then we start the sequence of observations. So it's a nice telescope. It is a little interesting because we are not only using it for, say, normal research, but also to try out new ideas and to develop new technologies. And we especially build it in a way that it has a wide field of view, so that we can search for interesting objects, which we then follow up with other bigger telescope. And so to some extent we are using it also as a viewfinder for other telescopes, and just to try out new equipment and new ideas. And for example, last year, together with Hamburg, Hamburg Observatory developed a new device how to measure the orientation of the spin axis of stars. And in principle, they want to bring this new equipment to the VLT, but of course they needed a telescope where they could develop it. So they came here and installed it in the Coude spectrograph, and we took first measurements just to show that the whole method works. And that's a typical application for the telescope, trying out new ideas and developing new equipment which can then be used in other telescopes. Then the third application is also, say, students' education. We are not that far from the University of Jena, and actually we teach at the University of Jena, and the students from there have the possibility to do really hands-on astronomy by really going here and carrying out projects and so on. And that's very attractive. We also offer these possibilities for students of other universities. The telescope is now a little bit more than 50 years old. It was commissioned in November 1960s. So we just had our 50-year anniversary where we made a big meeting and party and so on. And so it's in that sense, it's an old telescope. But on the other hand, it's a modern telescope because we renovated it. And
it has a second life now.
Yes, yes. And it's still very much like a classical telescope. It has a moving mass of 65 tons. So that's actually a lot. And the dome itself has a moving mass of 180 tons, 20 meters in diameter. So it's a very large equipment. And the other 2-meter telescope which exists in Germany is on Wendelstein, which is now 1 year old. It's nice to compare the two. For example, they have, as far as I remember, an 8-meter dome. So we have a 20-meter dome, and the other telescope, same aperture, has an 8-meter dome. So
I'm wondering how it fits.
Yes, yes. So the telescope is of course much shorter, and the dome is completely filled with this telescope. So in 50 years evolution and engineering, telescopes to some extent got much smaller of the same aperture.
It comes to be robotic, fully robotic.
Yes, 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 yes. And that is nice to compare the two. Then you see 50 years of development. The mirror itself is 2 meters in diameter. It weighs roughly 2 tons. And 24 centimeters, which is interesting. If you compare it to the mirrors of the VLT, they are just 18 centimeters. So this mirror is a classical one. It is thicker than today an 8-meter mirror. And of course, to some extent, if you start with a mirror that is very heavy, then the tube of the telescope has to be very heavy, and the mounting also has to be very heavy. So everything scales from the mass of the mirror. So if the mirror is thinner, then the whole telescope also becomes much more lightweight. To some extent, it looks, this is the one which is the telescope. This is the second one, where you can see, in principle, it's the biggest Schmidt corrector, which is a glass plate of the world. It's actually the prism, but the difference is hard to recognize. You see that there are double images, and so that is the one with a prism. But otherwise, it looks exactly the same as the one which is in the telescope at the moment.
And what is the diameter, working diameter?
1 meter 34. So 1 meter 34 is the diameter. And if I remember correctly, 300 kilograms of glass.